Welcome back, everyone. We're going to be talking about current limiting fuses today. So last week we covered a fair bit of ground. We talked about transformers and how they have a certain limit of exposure that they can take, and if they experience a current greater than a given value for a period of time, you'll expect that that transformer is damaged, known as a damage curve, and that was a formula that came from the IEEE. And then we also studied the upper bounds of customer behavior, which falls into this region here, which was defined by our inrush curve. And anything on this side of that line represented a normal customer behavior, and anything that crossed that line we're going to define as a fault condition, and how that gave us a certain area of margin in between those two lines where our protection can act. And in here we have this great 8T fuse, so it's a T-series fuse with an 8 amp rating on it, and it fits very nicely in between those two. So we have perfect coordination. The transformer is perfectly well protected. We have no chance that we're going to get a nuisance trip, and our transformer is protected everywhere except for down here. And what we run into is this problem where this period of time here is around 2/3 of a cycle. And because expulsion fuses require a zero crossing, and usually a second zero crossing before they can extinguish a fault, it's impossible for a current limiting fuse or an expulsion fuse to go any faster than that. And this creates a gap in our protection. For really, really high impulse currents, our expulsion fuses aren't fast enough to protect our transformers. And as I'm sure you can imagine, if you have a fault where the transformer burns out over here and you get damage to your transformer after 100 or 200 or 1,000 seconds, that's not great, but it's not likely to be the big kaboom. It's more likely to be the pop and the fizzle. If you manage to blow up a transformer and damage it in 16 thousandths of a second, you were delivering some serious energy to that transformer. And the likelihood that this failure over here is going to be energetic is very high. Energetic is code for blew the lid off of it and spilled flaming transformer oil all over 4 lots. So, the chances of bad stuff down here are much greater than the chances of bad stuff up here. And so the fact that we've got this gap in our protection is a problem. But expulsion fuses can't fix it, and so we need a new tool. And this is where our current limiting fuses come into play. So current limiting fuses are zero forcing or zero shifting. They don't need to wait for the next zero crossing to extinguish the fault arc and to put the fault out to end that current flow. They don't tend to have a functional maximum interrupting rating. So, like on the box, it says interrupts up to, typically 20,000 or 50,000 amps. But generally, most sources can't deliver 50,000 amps. So, again, big enough, it don't matter. Now, the nice thing about these is that because of the way they act, they reduce the peak current let through. So, we talked last week about how there's 2 big killers involved for our transformers when we have a fault. The first big killer we get is a magnetic effect, where the big current surge results in a big magnetic field, and the transformer will try to literally wrench itself apart. Cores get ripped off bases, coils crush down and destroy their own insulation. Leads get ripped off of bushings. All kinds of bad stuff can happen because of these strong magnetic fields. So if we can reduce the peak current, we can reduce those magnetic stresses as well. And then, that's going to help improve our survivability for our transformer. They also reduce, because they're zero forcing and they're dropping this peak current, they're letting less energy through. So less energy means less heating, right? Less time for that arc to do damage, because it's the heat from the arc. It's not the arc, it's the heat that causes the problems. So we're going to have less heat delivered, and we're going to have less magnetic forces available because of that reduced peak current. So good all the way around. Current limiting fuses are classified into one of three groups. There are backup fuses, which are designed to deal with high fault currents only, and that's what we're going to be using in our class. There are general purpose fuses, which are designed to clear most faults down to like the 1 hour long duration, chronic overload situation. And then there's a full range fuse, which is designed to deal with everything. Now, as you go from one classification to the other, these things tend to get much more complicated in their physical construction because they have to do more things. And as a result of that, they get much more expensive every time you go up. Which isn't a big deal if you only need to buy 2 of them, but becomes a big deal when you're talking about having to deploy thousands and thousands of them like you do in a distribution system. So let's take a look at how these things are constructed. So you start out with a fiberglass body, could be fiberboard, and it's arranged in this cross section. Right, you've got this X or this T-shaped cross section, and you're going to take that and you're going to wrap this slotted filament all the way around it. So the filament itself looks a lot like plumber's strapping, if you're familiar with it. If you've ever had the chance to see a dot matrix printer from the 80s, it also looks a lot like the edging that came off those printer papers. So you've got this thin filament here. This is like a metal foil, and it's got holes punched in it at a regular interval all the way along. And so you get this ribbon that is formed, and we take that ribbon, we're going to wrap it all the way around. Now, if you have a full range or a general purpose, you're going to have a low current element. So you'll have a second functioning fuse here, and this will be, melt away style, similar to the expulsion fuses that we studied yesterday. But you'll notice that these are fully capped. They're sealed at both ends. So there's no chance for things to be, we're not going to be shooting gases out or propelling a lead away. Instead, what we're going to do is we're going to take this ribbon wrapped around this cross-sectional piece. We're going to stuff it in the fuse body, and then we're going to pack it full of sand. All the openings here, there's no air, is densely packed with sand all the way to the top. So in the event that we get a fault, our filament wire, our ribbon, is going to melt. And it's going to melt at the spots with the lowest cross section. So it's going to melt here. But it's also going to melt here, and here, and here, and here, and here. And you get all kinds of little tiny arcs, whereas an expulsion fuse gets one great big arc. Here we have many small arcs. As the element melts in many spots all the way along. Now, we talked about how the temperature of the arc was really hot, right? Potentially 19,000 degrees Celsius. So that's more than hot enough to melt sand. And what do you get when you melt sand? You get glass. So glass being a rather lovely insulator. So what happens at each of these sites where you have an arc is your arc melts the sand directly around it, and the molten metal fuses with the molten sand, and you get this little glob of a material called fulgurite, which is sand and metal melted together and mixed up, which happens to have a really, really high resistance. And as it cools, its resistance gets even greater. And so what you end up doing is where before you had, this might have a resistance when it's in good shape, of 1 milliohm, it starts to burn and the fulgurite starts to form, and all of a sudden now it's 1 ohm, and then it's 10 ohms, and then it's 1,000 ohms, and then it's 1,000,000 ohms, and then it's 1,000,000,000 ohms. And so what it does is it ramps that resistance right up very quickly as time goes by. And if we take a look at what that looks like in time, we can see that things are normal, and then we get our fault. And with our expulsion fuse, our fault slams into the limit of the available fault current from the source, and then we have to wait. And the fault current, the expulsion fuse melts, and then it arcs and burns and burns and burns and burns, and then we get down to our zero crossing and we snuff it. And then we might have a second lobe where we get a respark. Oh, and then we got to burn some more, and then we'll try again to extinguish things. Current limiting fuse operates a lot different. Current limiting fuse, we get our fault, and then immediately, very, very shortly afterwards, our fuse melts. And then the current starts going up, but now the fulgurite's starting to form. We've got the glass mixing in with the metal where the arc is, and the resistance starts going up. And all of a sudden the fault current gets clamped off, and it doesn't keep going up any higher. And then, because the current isn't going up, it starts to cool, and the resistance at each one of those small arcs starts to go way up, and then the current falls, and then our arc is extinguished faster than our first half cycle would have occurred, and at a much lower peak current than would have occurred otherwise. So if you take a look at the energy delivered, so energy delivered is the area under the graph, it's the shaded section. You can see how much smaller the area is for a current limiting fuse. And this graphic uses ELF style current limiting fuses. You can see how much less surface area, that's less energy, that's less heat that's being delivered into those things. Whatever our faulted assets are. So significantly less energy, which is going to mean significantly less damage. So in this class, in our previous graph, we looked at an ELF FEM series fuse. For the purposes of this class, we're only going to be looking at a series of fuses known as the NX companion fuses. There are lots and lots of different current limiting fuses. They all do the exact same thing. So much like there are lots and lots of expulsion fuses, but we've limited ourselves to 2 series, the K and the T, for the purposes of this class. There's lots and lots of there's lots and lots of current limiting fuses as well, but we're going to limit ourselves to just a couple for the interest of keeping things straightforward for the class, because an ELF and an NX are going to do similar things, so we can prove the point without having to add a lot of extra complexity. So the NX companion fuses, a few things to take a look at. One, it's not a big series of fuses where we've got a dozen or more of Ks and Ts. We've got 3 NXs. The other thing to look at is that these things don't have a lot of low speed behavior, right? If these things are going to operate, they're going to operate in the first half a second, or they're not going to operate at all. The other thing, which is the important thing from our perspective, is that they don't have that long tail associated with them, right? So this is this lack of the tail that you would have seen otherwise on a current limit on an expulsion fuse. This is that zero forcing action. We can guarantee that from the time we start melting till the time we finish melting, it's going to have a fixed point in time. It's only going to take a certain amount of time. We don't end up with that long tail tapering off. So let's do an example. Let's illustrate how this works and how you compare an NX fuse with an expulsion fuse. So we'll take our transformer, 150 kVA, fed 16,000 volts. First thing we notice, our units, they don't match. So when we're calculating full load amps, we got to make sure we're in matched units. So you could go 16,000 volts could be 16 kVA, and you could put everything in kilo units. That's fine. For our purposes, we're going to express everything as base units. VA and V, that's fine too. Mixing and matching, not fine. You're going to get strange answers and it'll throw off all your calculations. So we're going to start with our inrush table. We're going to get that built. We have our times. These are all fixed. We have our multipliers. These are all defined as well. We're going to take that full load amp rating. We're going to plug it in down here. And we're going to figure out for this specific transformer, 245 amps at 100th of a second would be considered our inrush limit. And we're able to build out the table in seconds and amps. So we're able to put that on a TCC chart. After that, we're going to build our damage curve. We've got our equation that we have that the IEEE defined, which is the damage curve limit. And we're going to keep in mind that we're going to stop at 100 seconds. We're going to take some measurements here. We'll pick some times. You don't have to pick these times, but you might as well pick these as they're very easy to find on a TCC graph. It's the major divisions. So you can pick other times. They'll work fine too with this equation, but you're making life hard on yourself. So to what end? We use our equation, we plug in our T's, we get our I's, keeping in mind that I is per unit, so it acts as a multiplier. And we'll take that, we'll apply our full load amp rating, we'll multiply everything out, and we get our currents in amps. So now we can put this on a TCC curve as well. So bringing things over, we're going to start out. We've got our TCC graph here. We've got all our T-speed fuses. And it's time for us to start plotting our inrush and our damage curves on the graph. So we're going to start out. Time of 1/100th of a second. We're going to 245 amps. So we can see here we've got 100, 200, 45, keeping in mind that 3 is near the 50% marker and 5 is near the 75% marker. So we're going to call that right about there. And then at our next unit, we are at 112. So we're going to call that right about there. Sloppy. And we'll go to 56. $40, 56 should be about here. And we carry on building out the table. When we're done with that, we're going to plot our damage curve. Keeping in mind, if we have the flexibility that we can do things in full color, our damage curve should be red and our inrush curve should be black. So we're at 3,314 amps. We're going to zoom in a little bit. We're at 2,000, 3,000, 3,300 should be pretty much directly in the middle between 3 and 4,000. And then we'll be at 1/10 of a second. We're at 1,048. 331. Again, that should be about the 50% marker in between the two. And we carry on plotting our points up the graph. We draw a straight line between them, play connect the dots, and here we are. We can see our inrush and our damage lines. Keep in mind your damage line should be straight. If your damage line is not straight, it means something's gone wrong. Go and check where you plotted your points. Your inrush curve should be pretty straight with the exception of this elbow between the 10 and the 900. That is an elbow, but the rest of these should be straight. If they're not straight, check your points. Something went wrong. And we can see of all the fuses, only the 12T sits in between here so nice and clean. It doesn't run into issues here. There's lots of space between the 12T and the inrush curve, so that's good. And we don't get ourselves into too much trouble until way down here where we cross over with that damage curve like we will with all of our expulsion fuses. So 12T looking good. Now we'll go and we'll classify our NX. So we're going to start out. We've got our damage and inrush table. We have to plot our points. Again, same thing we did the first time. So we'll go 245 with the black ink, 245 should be about here. We'll do 112, should be about here. And we'll do 56. Be about here. You can see a straight lines forming, so that's a good sign that I'm on the right track. You can keep going upwards, but for these NX fuses, there's no need to finish drawing the line. And then we'll go to our high speed side. 2, 3, oops, in red, because we have that flexibility here. That's getting kind of close. We're at 1,000. 330. We're forming a straight line there. Again, that's looking promising. So let's finish plotting those. Now, it's possible, so generally what you want, current limiting fuses are expensive. Expulsion fuses, relatively cheap. So if you have two current limiting fuses, in this case the 12 obviously fits in between, and the 25 fits entirely in between. And it's possible that depending exactly where we get into trouble with our expulsion fuse, we might be able to make the 40 work, although it is darn tight. So we'll disqualify the 40 for now. But if we take a look at the 12 and the 25, if you have two choices on a current limiting fuse, unless you have a reason to not do it, always pick the bigger one. This is going to allow the expulsion fuse to handle a greater variety of faults. The expulsion fuse is easier to troubleshoot and it's less expensive. So a win from operations and a win for engineering. So if we're taking up our pick and you have a situation like this where the 12 is good and the 25 is good, pick the bigger of the two unless you have a specific reason why you can't. So if we take these out and we just plot the two fuses, what we end up with is this line here for a maximum clear. And so, as the current comes up, as time rushes by, we can see expulsion fuse operates, expulsion fuse operates, expulsion fuse, expulsion fuse, expulsion fuse. All along, the expulsion fuse is trying to operate. And then we get down here, expulsion fuse operates. And then we get here, and the expulsion fuse starts, but now the current limiting fuse starts to operate as well. And now the current limiting fuse has extinguished the fault before the expulsion fuse has had a chance to finish doing its job as well. And so what happens is the current limiting fuse, in practice, cuts off the tail of that expulsion fuse. So this whole part of the current limiting fuse's curve will never get used because the expulsion fuse will have always operated first. But here we can see the current limiting fuse is going to protect us for those very, very high current faults, and it does that by effectively cutting the tail off of our expulsion fuse. So some conclusions. Expulsion and current limiting fuses are complementary in their function. And expulsion fuses, they are functionally a full range fuse, except for those really high intensity faults where they fall down. And by pairing an expulsion fuse with a current limiting fuse, we can cover ourselves from top to bottom. Because of this, you're always going to find them working in a pair when you're talking about transformer protection. Now, you may say, but Matt, I've looked at the, overhead can, and there's only one fuse holder, and you'd be absolutely right. Sometimes current limiting fuses are mounted in external holders, so sometimes that cutout, that fuse in the mounted cutout actually has two separate fuses in one body. But more often than not, the current limiting fuse, because it's not designed to operate in any but the most dire situation, is actually going to be mounted under oil. So for an overhead can, you'd have to take the lid off to access that fuse. For a pad mount, there'd be a cover plate that would show you'd need to remove to access that fuse. Looking forward to talking to you guys next week, and we'll talk soon.